Electrochemistry is a fascinating field that delves into the conversion of chemical energy into electrical energy and the reverse process. This discipline is essential for both theoretical understanding and practical applications, impacting various industries and technologies. By studying electrochemistry, scientists can harness the energy released during spontaneous chemical reactions to produce electricity and utilize electrical energy to drive non-spontaneous chemical transformations. One of the most significant contributions of electrochemistry is the production of a wide range of chemicals. Metals, sodium hydroxide, chlorine, and fluorine are just a few examples of substances produced through electrochemical methods. These processes are not only efficient, but also environmentally friendly, making them crucial for developing sustainable technologies. Batteries and fuel cells are prime examples of electrochemical devices that convert chemical energy into electrical energy. They are widely used in various instruments and devices, from smartphones to electric vehicles. The reactions that occur in these systems can be energy efficient and less polluting compared to traditional methods. As the world shifts towards greener technologies, the study of electrochemistry becomes increasingly important for creating eco-friendly solutions. The Daniell cell serves as a classic illustration of electrochemical principles. This cell converts the chemical energy released during the redox reaction of zinc and copper into electrical energy, producing an electrical potential of 1.1 volts when the concentrations of zinc and copper ions are equal to 1 molar. In this setup, zinc solid reacts with copper ions in solution, resulting in the formation of zinc ions and solid copper. When an external opposing voltage is applied to the Daniell cell and gradually increased, the spontaneous reaction continues until the opposing voltage reaches 1.1 volts. At this point, the reaction halts and no current flows through the cell. However, if the external potential is increased beyond this threshold, the reaction reverses direction, transforming the cell into an electrolytic cell. In this mode, electrical energy is used to drive non-spontaneous chemical reactions. A galvanic cell, like the Daniell cell, is an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into electrical energy. In this device, the Gibbs energy of the spontaneous reaction is transformed into electrical work, which can be harnessed to power various electrical gadgets, including motors, heaters, fans, and geysers. The Daniell cell operates through a specific redox reaction. Zinc solid reacts with copper ions in solution, yielding zinc ions and solid copper. This overall cell reaction is the sum of two half reactions. The reduction half reaction occurs when copper ions gain electrons to become solid copper, while the oxidation half reaction involves zinc solid losing electrons to form zinc ions. These half reactions take place in two distinct portions of the Daniell cell, known as half cells or redox couples. The copper electrode serves as the reduction half cell, where the reduction reaction occurs, while the zinc electrode acts as the oxidation half cell. This separation allows for the efficient transfer of electrons between the two electrodes. Constructing galvanic cells based on the Daniell cell model is possible by combining various half cells. Each half cell consists of a metallic electrode immersed in an electrolyte solution. The two half cells are connected externally by a metallic wire, often incorporating a voltmeter and a switch. Internally, the electrolytes of the two half cells are connected through a salt bridge, which maintains electrical neutrality by allowing ions to flow between the half cells. In some cases, both electrodes may be submerged in the same electrolyte solution, eliminating the need for a salt bridge. At the interface between the electrode and electrolyte, metal ions from the solution tend to deposit onto the electrode, creating a positive charge. Simultaneously, metal atoms from the electrode may dissolve into the solution as ions, leaving behind electrons and generating a negative charge. This charge separation leads to the development of electrode potential, defined as the potential difference between the electrode and the electrolyte. When the concentrations of all species involved in a half cell are equal to 1 molar, the electrode potential is referred to as the standard electrode potential. According to IUPAC conventions, standard reduction potentials are now known as standard electrode potentials. In a galvanic cell, the half cell where oxidation occurs is designated as the anode, which possesses a negative potential relative to the solution. Conversely, the half cell where reduction takes place is termed the cathode, exhibiting a positive potential. This potential difference between the two electrodes drives the flow of electrons when the circuit is completed. Electrons flow from the anode to the cathode, while the direction of current flow is opposite to that of electron flow. The cell potential, measured in volts, represents the difference between the electrode potentials of the cathode and anode. This potential is known as the cell electromotive force, EMF, when no current is drawn from the cell. In standard representations of galvanic cells, the anode is placed on the left and the cathode on the right. A vertical line is used to separate the metal from the electrolyte solution, while a double vertical line indicates the connection between the two electrolytes through a salt bridge. Electrochemistry's vast applications and interdisciplinary nature underscore its significance in advancing technology and sustainability. As researchers continue to explore new electrochemical methods, the potential for innovation in energy storage, conversion, and environmental protection remains limitless. The individual half-cell potential is a fascinating concept in electrochemistry, but it cannot be measured directly. Instead, what can be measured is the difference between the potentials of two half cells, which ultimately gives the electromotive force, or EMF, of the entire electrochemical cell. This means that by selecting a reference point, the potential of one electrode can be determined relative to another. In electrochemical systems, the standard hydrogen electrode, SHE, is conventionally assigned a potential of 0 volts at all temperatures. This reference electrode is crucial for measuring other half-cell potentials. The SHE consists of a platinum electrode coated with platinum black, immersed in an acidic solution. Pure hydrogen gas is bubbled through this solution, ensuring that the concentration of both the reduced form, H2 gas, and the oxidized form, H+ ions, is maintained at unity. Specifically, this means that the pressure of hydrogen gas is set at 1 bar, and the concentration of hydrogen ions in the solution is kept at 1 molar. At a temperature of 298 K, when the SHE is used as an anode and another half cell is used as a cathode, the EMF measured provides the reduction potential of that second half cell. If the concentrations of the oxidized and reduced forms in the right-hand half cell are also unity, the cell potential equals the standard electrode potential, EDIC, of the given half cell. Understanding the implications of standard electrode potentials is essential. For example, a positive value indicates that copper ions, Cu2+, are reduced more easily than hydrogen ions, H+. This means that under standard conditions, hydrogen ions cannot oxidize copper. In simpler terms, hydrogen gas can reduce copper ions. This is why copper does not dissolve in hydrochloric acid. However, in nitric acid, copper is oxidized by nitrate ions instead of hydrogen ions, showcasing the selective reactivity of different acids. On the other hand, a negative standard electrode potential suggests that hydrogen ions can oxidize zinc. This means that zinc can effectively reduce hydrogen ions, demonstrating its reactivity in electrochemical processes. In electrochemical cells, inert electrodes like platinum or gold are often used. These electrodes do not participate in the chemical reactions occurring in the cell, but provide a surface for oxidation or reduction reactions and facilitate the conduction of electrons. This is particularly useful in various applications where the electrode material should not interfere with the reaction being studied. The significance of standard electrode potentials cannot be overstated. They provide valuable insights into the stability of different species in electrochemical reactions. If the standard electrode potential of an electrode is greater than 0, it indicates that its reduced form is more stable compared to hydrogen gas. Conversely, a negative standard electrode potential implies that hydrogen gas is more stable than the reduced form of the species in question. For instance, fluorine has the highest standard electrode potential, indicating that it has the maximum tendency to get reduced to fluoride ions, F. This makes fluorine gas the strongest oxidizing agent, while fluoride ions are the weakest reducing agents. On the other end of the spectrum, lithium has the lowest electrode potential, suggesting that lithium ions are the weakest oxidizing agents, whereas lithium metal is the most powerful reducing agent in aqueous solutions. As one examines the standards electrode potentials in a table, a trend becomes apparent. As one moves from the top to the bottom, the standard electrode potential decreases. This decrease corresponds to a reduction in the oxidizing power of the species on the left side and an increase in the reducing power of the species on the right side of the reaction. Electrochemical cells are extensively utilized for various applications, including determining the pH of solutions, calculating solubility products, evaluating equilibrium constants, and conducting potentiometric titrations. These cells play a crucial role in analytical chemistry and industrial processes, showcasing the practical importance of understanding electrode potentials. The Nernst equation is another vital concept in this context. It is essential to note that the previous discussions assumed that the concentration of all species involved in the electrode reaction is unity. However, this is not always the case in real-world applications. The Nernst equation demonstrates how the cell potential, E, depends on the concentrations of the ions involved, such as copper, Cu2+, and zinc, Zn2+. As the concentration of copper ions increases and the concentration of zinc ions decreases, the cell potential changes accordingly. In a Daniell cell, for instance, when the circuit is closed, the reaction occurs, solid zinc reacts with aqueous copper ions to produce aqueous zinc ions and solid copper. Over time, the concentration of zinc ions increases, while that of copper ions decreases. This change affects the voltage of the cell, which can be monitored using a voltmeter. Eventually, a point is reached where there is no further change in the concentrations of copper and zinc ions, and the voltmeter reads 0. This indicates that equilibrium has been attained in the system. The Nernst equation thus provides a relationship between the equilibrium constant of the reaction and the standard potential of the cell in which that reaction takes place. This relationship allows for the calculation of equilibrium constants, which can be challenging to measure otherwise, using the corresponding EDEG value of the cell.
Electrochemical cell and Gibbs energy of the reaction. Electrical work done in 1 second is equal to electrical potential multiplied by total charge passed. If we want to obtain maximum work from a galvanic cell, then charge has to be passed reversibly. The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy, and therefore, if the EMF of the cell is E and NF is the amount of charge passed and delta Rg is the Gibbs energy of the reaction, then delta Rg is equal to NFE cell. It may be remembered that E cell is an intensive parameter, but delta Rg is an extensive thermodynamic property, and the value depends on N. Thus, from a measurement of E0 cell, we can obtain an important thermodynamic quantity, delta Rg0 standard Gibbs energy of the reaction. From the latter, we can calculate equilibrium constant by the equation, delta Rg0 equals to minus Rt and K. Conductance of electrolytic solutions. The electrical resistance is represented by the symbol R, and it is measured in ohm, which in terms of SI base units is equal to kilogram meter square divided by S cubed and a square. It can be measured with the help of a Wheatstone bridge. The electrical resistance of any object is directly proportional to its length, L, and inversely proportional to its area of cross-section, A. The constant of proportionality Greek, rho, is called resistivity or specific resistance. Its SI units are ohm meter, and quite often its submultiple, ohm centimeter, is also used. IUPAC recommends the use of the term resistivity over specific resistance. Physically, the resistivity for substance is its resistance when it is 1 meter long and its area of cross-section is 1 meter square. The inverse of resistance, R, is called conductance, G.
The SI unit of conductance is Siemens, represented by the symbol S, and is equal to ohm inverse, also known as MHO. The inverse of resistivity, called conductivity or specific conductance, is represented by the symbol Greek kappa. IUPAC has recommended the use of term conductivity over specific conductance. The SI unit of conductivity is S divided by M. Conductivity of a material is its conductance when it is 1 m long and its area of cross-section is 1 square meter. The magnitude of conductivity varies a great deal and depends on the nature of the material. It also depends on the temperature and pressure at which the measurements are made. Materials are classified into conductors, insulators, and semiconductors depending on the magnitude of their conductivity. Metals and their alloys have very large conductivity and are known as conductors. Certain non-metals like carbon black, graphite, and some organic polymers are also electronically conducting. Substances like glass, ceramics, etc., having very low conductivity are known as insulators. Substances like silicon, doped silicon, and gallium arsenide having conductivity between conductors and insulators are called semiconductors and are important electronic materials. Certain materials called superconductors by definition have zero resistivity or infinite conductivity. Earlier, only metals and their alloys at very low temperatures from 0 to 15 K were known to behave as superconductors, but nowadays a number of ceramic materials and mixed oxides are also known to show superconductivity at temperatures as high as 150 K. Electrical conductance through metals is called metallic or electronic conductance and is due to the movement of electrons. The electronic conductance depends on I, the nature and structure of the metal, 2, the number of valence electrons per atom, 3, temperature, it decreases with increase of temperature. As the electrons enter at one end and go out through the other end, the composition of the metallic conductor remains unchanged.
We know that accurate measurement of an unknown resistance can be performed on a Wheatstone bridge. However, for measuring the resistance of an ionic solution, we face two problems. Firstly, passing direct current, DC, changes the composition of the solution. Secondly, a solution cannot be connected to the bridge like a metallic wire or other solid conductor. The first difficulty is resolved by using an alternating current, AC, source of power. The second problem is solved by using a specially designed vessel called conductivity cell. Basically, a simple design is created which consists of two platinum electrodes coated with platinum black. Finely divided metallic point is deposited on the electrodes electrochemically. These have area of cross-section equal to and are separated by distance L. Therefore, solution confined between these electrodes is a column of length L and our area of cross-section A. The resistance of such a column of solution is then given by the equation, R equals to rho multiplied by L and divided by A, which is equal to L divided by kappa into A. The quantity L divided by A is called cell constant, denoted by the symbol G star. It depends on the distance between the electrodes and their area of cross-section and has the dimension of length, 1, and can be calculated if we know L and A. Measurement of L and A is not only inconvenient, but also unreliable. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solutions whose conductivity is known accurately at various concentrations. The cell constant, G star, is then given by the equation. G star equals to L multiplied by A, which is again equal to R multiplied by kappa. Once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup to measure resistance or conductivity consists of two resistances R3 and R4, a variable resistance R1, and the conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by an oscillator O, a source of AC power in the audio frequency range 550 to 5,000 cycles per second. P is a suitable detector, a headphone or other electronic device, and the bridge is balanced when no current passes through the detector. Under these conditions, unknown resistance R2 equals to R1 multiplied by R4 and divided by R3. These days, inexpensive conductivity meters are available which can directly read the conductance or resistance of the solution in the conductivity cell. Once the cell constant and the resistance of the solution in the cell is determined, the conductivity of the solution is given by the equation. Conductivity kappa equals to cell constant G star divided by the resistance R. The conductivity of solutions of different electrolytes in the same solvent and at a given temperature differs due to charge and size of the ions in which they dissociate, the concentration of ions or ease with which the ions move under a potential gradient. It therefore becomes necessary to define a physically more meaningful quantity called molar conductivity, denoted by the symbol Lm, Greek, lambda. It is related to the conductivity of the solution by the equation, molar conductivity kappa divided by C. If we use S divided by Cm as the units for K and mole Cm to the power of -3, the units of concentration, then the units for lambda m are SCm squared mole to the power of -1. Variation of conductivity and molar conductivity with concentration. Both conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity always decreases with decrease in concentration both for weak and strong electrolytes. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution kept between 2 platinum electrodes with unit area of cross-section and at a distance of unit length. This is clear from the equation G equals to kappa A divided by L, which is equal to kappa. Both A and L are unity in their appropriate units in m or cm. Molar conductivity of solution at a given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte kept between 2 electrodes with area of cross-section A and distance of unit length. Molar conductivity increases with decrease in concentration. This is because the total volume V of solution containing 1 mole of electrolyte also increases. It has been found that decrease in K on dilution of a solution is more than compensated by increase in its volume. Physically, it means that at a given concentration, Lm can be defined as the conductance of the electrolytic solution kept between the electrodes of a conductivity cell at unit distance, but having area of cross-section large enough to accommodate sufficient volume of solution. That contains 1 mole of the electrolyte. When concentration approaches 0, the molar conductivity is known as limiting molar conductivity and is represented by the symbol lambda 0m. The variation in lambda m with concentration is different for strong and weak electrolytes. For strong electrolytes, lambda m increases slowly with dilution. Kohlrausch examined lambda 0m values for a number of strong electrolytes and observed certain regularities. He noted that the difference in lambda 0m of the electrolytes Nax and Kx for any x is nearly constant. In general, if an electrolyte on dissociation gives N plus cations and N anions, then its limiting molar conductivity is given by lambda 0m equals to V plus lambda 0 plus added to V minus lambda 0 minus. Lambda 0 plus and lambda 0 minus are the limiting molar conductivities of the cation and anion respectively. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentrations, and hence, for such electrolytes, the change in Lm with dilution is due to increase in the degree of dissociation. Consequently, the number of ions in total volume of solution that contains 1 mole of electrolyte increases. In such cases, lambda m increases steeply on dilution, especially near lower concentrations. Therefore, lambda 0m cannot be obtained by extrapolation of lambda m to 0 concentration. At infinite dilution, that is concentration C tends to 0, electrolyte dissociates completely, but at such low concentration, the conductivity of the solution is so low that it cannot be measured accurately. Therefore, lambda 0m for weak electrolytes is obtained by using Kohlrausch law of independent migration of ions. At any concentration C, if alpha is the degree of dissociation, then it can be approximated to the ratio of molar conductivity Lm at the concentration C to limiting molar conductivity, lambda 0m. Using Kohlrausch law of independent migration of ions, it is possible to calculate lambda 0m for any electrolyte from the lambda 0 of individual ions. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know the lambda 0m and lambda m at a given concentration C. Electrolytic cells and electrolysis. In an electrolytic cell, external source of voltage is used to bring about a chemical reaction. The electrochemical processes are of great importance in a laboratory and the chemical industry. One of the simplest electrolytic cell consists of 2 copper strips dipping in an aqueous solution of copper sulfate. If a DC voltage is applied to the 2 electrodes, then copper 2 plus ions discharge at the cathode, which is negatively charged. Thus, copper is dissolved, oxidized at anode, and deposited, reduced, at cathode. This is the basis for an industrial process in which impure copper is converted into copper of high purity. The impure copper is made an anode that dissolves on passing current, and pure copper is deposited at the cathode. Many metals like Na, Mg, Al, etc. are produced on large scale by electrochemical reduction of their respective cations, where no suitable chemical reducing agents are available for this purpose. Sodium and magnesium metals are produced by the electrolysis of their fused chlorides, and aluminium is produced by electrolysis of aluminium oxide in presence of cryolite. Michael Faraday was the first scientist who described the quantitative aspects of electrolysis. After his extensive investigations on electrolysis of solutions and melts of electrolytes, Faraday published his results during 1833 to 34 in the form of the following well-known Faraday's two laws of electrolysis. 1. First law: the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte, solution, or melt. 2. Second law: the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Atomic mass of metal divided by the number of electrons required to reduce the cation. There are no constant current sources available during Faraday's times. The general practice was to put a coulometer, a standard electrolytic cell, for determining the quantity of electricity passed from the amount of metal, generally silver or copper, deposited or consumed. We now have constant current, I, sources available, and the quantity of electricity Q passed is given by Q equals to I multiplied by the time T, which is in seconds. The amount of electricity, or charge, required for oxidation or reduction depends on the stoichiometry of the electrode reaction. The charge or amount of electricity on 1 mole of electrons is called Faraday and is represented by the symbol F. For approximate calculations, we use 1 Faraday is approximately equal to 96,500 C per mole. The charge passed through the electrolytic cell during electrolysis is equal to the product of current in amperes and time in seconds. In commercial production of metals, current as high as 50,000 amperes are used at amounts to about 0.518 Faradays per second. Products of electrolysis depend on the nature of material being electrolyzed and the type of electrodes being used. If the electrode is inert, e.g., platinum or gold, it does not participate in the chemical reaction and acts only as source or sink for electrons. On the other hand, if the electrode is reactive, it participates in the electrode reaction. Thus, the products of electrolysis may be different for reactive and inert electrodes. The products of electrolysis depend on the different oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Moreover, some of the electrochemical processes, although feasible, are so slow kinetically that at lower voltages these do not seem to take place, and extra potential, called overpotential, has to be applied, which makes such process more difficult to occur. For example, if we use molten sodium chloride, the products of electrolysis are sodium metal and chlorine gas. Here we have only 1 cation, which is reduced at the cathode, and 1 anion, which is oxidized at the anode. During the electrolysis of aqueous sodium chloride solution, the products are sodium hydroxide, chlorine, and hydrogen. Batteries. Any battery, actually it may have one or more than one cell connected in series, or cell that we use as a source of electrical energy, is basically a galvanic cell where the chemical energy of the redox reaction is converted into electrical energy. However, for a battery to be a practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. There are mainly 2 types of batteries. In the primary batteries, the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused again. The most familiar example of this type is the dry cell, known as Leclanche cell after its discoverer, which is used commonly in our transistors and clocks. The cell consists of a zinc container that also acts as anode, and the cathode is a carbon graphite rod surrounded by powdered manganese dioxide and carbon. The space between the electrodes is filled by a moist paste of ammonium chloride and zinc chloride. The electrode reactions are complex. In the reaction at cathode, manganese is reduced from the +4 oxidation state to the +3 state. The cell has a potential of nearly 1.5 volts. Mercury cell, suitable for low current devices like hearing aids, watches, etc., consists of zinc, mercury amalgam as anode, and a paste of mercury oxide and carbon as the cathode. The electrolyte is a paste of potassium hydroxide and zinc oxide. The cell potential is approximately 1.35 V and remains constant during its life, as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime. Secondary cells. A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. A good secondary cell can undergo a large number of discharging and charging cycles. The most important secondary cell is the lead storage battery commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead packed with lead dioxide as cathode. A 38% solution of sulfuric acid is used as an electrolyte. Another important secondary cell is the nickel-cadmium cell, which has longer life than the lead storage cell, but more expensive to manufacture. We shall not go into details of working of the cell and the electrode reactions during charging and discharging. Fuel cells. Production of electricity by thermal plants is not a very efficient method and is a major source of pollution. In such plants, the chemical energy, heat of combustion, of fossil fuels, coal, gas, or oil is first used for converting water into high-pressure steam. This is then used to run a turbine to produce electricity. We know that a galvanic cell directly converts chemical energy into electricity and is highly efficient. It is now possible to make such cells in which reactants are fed continuously to the electrodes and products are removed continuously from the electrolyte compartment. Corrosion. Corrosion slowly coats the surfaces of metallic objects with oxides or other salts of the metal. The rusting of iron, tarnishing of silver, development of green coating on copper and bronze are some of the examples of corrosion. It causes enormous damage to buildings, bridges, ships, and to all objects made of metals, especially that of iron. We lose crores of rupees every year on account of corrosion. In corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxides. Corrosion of iron, commonly known as rusting, occurs in presence of water and air. The chemistry of corrosion is quite complex, but it may be considered essentially as an electrochemical phenomenon. At a particular spot of an object made of iron, oxidation takes place and that spot behaves as anode. Electrons released at an anodic spot move through the metal and go to another spot on the metal and reduce oxygen in the presence of hydrogen plus, which is believed to be available from carbonic acid formed due to dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from the atmosphere. This spot behaves as cathode. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which come out as rust in the form of hydrated ferric oxide and with further production of hydrogen ions. Prevention of corrosion is of prime importance. It not only saves money, but also helps in preventing accidents such as a bridge collapse or failure of a key component due to corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of the metallic object to come in contact with atmosphere. This can be done by covering the surface with paint or by some chemicals, e.g. bisphenol. Another simple method is to cover the surface by other metals such as zinc, tin, etc., that are inert or react to save the object. An electrochemical method is to provide a sacrificial electrode of another metal, like magnesium, zinc, etc., which corrodes itself but saves the object. Hydrogen energy. At present, the main source of energy that is driving our economy is fossil fuels, such as coal, oil, and gas. As more people on the planet aspire to improve their standard of living, their energy requirement will increase. In fact, the per capita consumption of energy used is a measure of development. Of course, it is assumed that energy is used for productive purpose and not merely wasted. We are already aware that carbon dioxide produced by the combustion of fossil fuels is resulting in the greenhouse effect. This is leading to a rise in the temperature of the Earth's surface, causing polar ice to melt and ocean levels to rise.